Thank you very much for the invitation. I explained when I agreed to give this talk that because I've been rather busy running the department this last term, I didn't have time to write a fresh talk. So what I've done is I'm recycling a couple of old talks. This first one is from a conference from a couple of years ago. And then the second one is actually part of a lecture course, which I give here in Oxford. Please do stop me at any point to ask questions. Don't save them up for the end. So yes, it's been 15 years now. My original multi-level paper I wrote in 2016 came out in the journal in 2018, and over the past 15 years, multi-level's been taken up by a lot of different groups around the world. In many cases, doing things I would never have imagined in terms of new application areas. And so these two talks are two of the things that I and my students, colleagues have been looking at in the last couple of years. This first talk is joint work with my student Oliver Sheridan Medton. He's now actually finished his PhD working at a hedge fund in Switzerland. And as it says, this is all about using approximate random numbers in Monte Carlo simulations, and again, bringing in multi-level. I suspect quite a few people in the audience probably know about multi-level already. If not, don't worry, I will be giving an introduction as I get into this talk. Okay, so that's the overview. Oh, I should also say that I've put these slides online on my webpage where I give all of my talks, so you can get those there. Okay, I prepared this conference talk for a very general audience, and so it just starts from the basics. Monte Carlo simulation is fundamentally a very simple-minded idea that you want to estimate the expected value of some output quantity P arising from a stochastic simulation, and you simply take the average of n independent samples of that. And to get a root mean square accuracy of epsilon requires that you use a number of samples of the order of epsilon to the minus 2 times the variance of a single sample. And so if each sample has a cost of c, then the total computational cost is approximately epsilon to the minus 2 v times c. So multi-level Monte Carlo, if we start with just 2 levels, the idea is that if there's some other quantity p tilde, which is approximately equal to p, but there is a bit of a difference there, then what we really want, which is the expected value of p, can be decomposed into the expected value of p tilde plus the expected correction, p minus p tilde. And so instead, what we can do, rather than directly applying Monte Carlo to the left-hand side, we apply it independently to each of the expectations on the right-hand side. And so we have an average using n0 samples of the p tilde, and then an average using n1 samples of the difference between p and p tilde. The combined cost of that estimator is clearly n0 times c0, c0 being the cost of doing p tilde, plus n1 times c1, with c1 being the cost of the difference. The variance, as given here, is V0 over N0 plus V1 over N1. And then we can look at, well, what do we need to do to minimize the total cost, subject to the fact that we want the overall accuracy, again, to have a root mean square accuracy of epsilon. And then that gives us this expression for the total costs. So this is just doing a constrained optimization for the integers n0 and n1 as if they're real variables. So we get that total cost expression. And in particular, just to give an example, if C0 is 1/10 of C, and C1 is C, the cost of coming up with that P value, the sample. So if P tilde is just 10% of the cost, the V0 is the same as the original variance, but the variance of the difference, V1, that's 0.1% of the original variance. Okay, so that gives you a sense of how, the degree to which P tilde is quite a reasonable approximation of P, but it's far from being perfect. Then if you plug that into the total cost expression, we end up with a factor 8, roughly, savings compared to the original Monte Carlo. Okay. This is sort of, these numbers are roughly indicative of what I'll be getting onto later when doing the approximate random variables. Then the multi-level idea builds on that with lots of levels where we have a sequence of approximations, p hat 0, p hat 1, so on, which approach the true quantity of interest p. And in my original paper, this was in the context of approximating the solution of a stochastic differential equation, where p hat L would correspond to a simulation using 2 to the capital L time steps on level L. So as L increases, it's giving you a more and more accurate approximation to P, but at more and more computational cost. And so in this case, we have the expected value of P hat capital L. This is a sufficiently fine approximation so that this expected value is close to being the true expected value. And then that decomposes into this telescoping sum, where we have the expected value of p hat 0, which might perhaps, in this case, only have one time step for the entire time interval, plus this set of expected corrections. And using independent estimation for each one of the expected corrections leads to the multi-level estimator, where again on level 0, we have an average over n0 samples of p hat 0. And then on each of the other levels, we use a different number of samples, n sub L. And these differences between p hat L and p hat L minus 1, where the superscript L comma n indicates the fact that for each level of simulation, we're looking at the differences independently of the differences on other levels. So that's the point of having the L. And the fact that we have the same n here corresponds to the fact that we're using, in some sense, the same stochastic sample to simulate both the level L and the level L minus 1 sample. And if we do that, then we end up with this expression for the overall cost once we again optimize the number of samples on the different levels to minimize the computational cost for a given overall accuracy. And then this led into the original paper, which came out in 2008 in Operations Research, that given this sort of geometric sequence of levels, where we assume these properties that the weak error, the expected difference between p hat L and the true p, is decreasing with level, so 2 to the minus alpha L, so alpha is the rate of weak convergence, that on each level we have an estimator y hat which has the desired expected value. So on level 0, it's just the base value. On the higher levels, it's a correction. Then we have this crucial one, that the variance of y hat is decreasing with level, controlled by this parameter beta. So this reflects the fact that as we go to higher and higher levels, we're getting a more and more accurate approximation. And correspondingly, the expected cost of the samples increases with level at a rate so controlled or given by gamma. And so beta and gamma are really the two key parameters here. Beta controls how quickly the variance goes to 0. Gamma controls how quickly the cost increases. And this sort of meta theorem says that if we have an application that satisfies those conditions, then the overall multi-level estimator, summing up these estimates for the corrections on each of the levels, achieves a root mean square error of epsilon with an expected computational cost that has this bound. That if beta is greater than gamma, it's just epsilon to the minus 2, which is sort of the best that you'd expect from Monte Carlo simulation. If beta is equal to gamma, we get this extra log epsilon squared term. And if beta is less than gamma, which generally I try to avoid if possible, we get this more complicated expression, but it's still better than plain Monte Carlo. Okay, so that's sort of an introduction to multi-level for those who've maybe not met it before. So what I was interested in this piece of research that Oliver did for his PhD was the possibility that we can approximate the random numbers which we use in carrying out a simulation. I was particularly interested thinking about mathematical finance applications where we might be interested in simulating the increments of a Levy process, or in finance, there's a model called the CIR model in which we are using increments of a non-central chi-squared distribution, which is a sort of expensive thing to simulate exactly. And so, thinking about the potential for having cheaper approximations to samples from these distributions. However, directly going to those, we would have real challenges, I think, doing the numerical analysis. And so this research looked at what happened if we used approximate normal random variables, where it turned out we were able to do the numerical analysis as well as doing the computations. So Klaus Ritter and colleagues at TU Kaiserslautern had already done some research in this area. I'd been involved with them to some degree in this. But this is sort of following on from that work. Now, before I do the next slide, I need to explain this last piece. This is one of those things that either seems obvious or seems confusing. One of the ways in which you can generate samples of a scalar random variable capital X is you first generate a uniform random value between 0 and 1, and then you invert the cumulative distribution function for X. Okay, so define capital X to be C inverse of U. What this means is, suppose you have a large population of people. If you pick a person at random, the probability that they're in, the oldest 1% is 1%. The probability of them being in the youngest 1% is 1%. Middle 1%, it's a 1% probability. So each of the percentiles is equally likely. So we're using a uniform random variable to pick out which percentile we want, and then we're inverting the cumulative distribution function to get the sample capital X. So it's one of the classic ways of generating random variables. So if we think now about what we want to do in approximating a stochastic differential equation, then, okay, so I've not actually written the SDE here, but it's, dx is equal to drift A dt plus volatility B times dw, where dw is the increment of a Brownian motion. So when we discretize that with an Euler-Maruyama approximation, we get x at the new time is equal to x at the old time plus the drift function A times the time step h plus the volatility B times the Brownian increment. And the Brownian increment has 0 mean and standard deviation equal to square root of h. And so we replace that by square root of h times z, where z is a unit normal random variable. And that is generated by taking the inverse of the normal CDF function applied to a uniform random variable. Okay, so that's the standard way of approximating a scalar and SDE. And what we were interested in is what happens if we replace the phi inverse here by an approximation Q tilde, some other function to approximate the inverse of the normal CDF. And there were three particular approximations that Oliver looked at in the work. One is what's known as a quantized approximation. So here on the left, we have both z and z tilde as a function of u being the uniform random variable from 0 to 1. And so the dashed line is the exact distribution or the exact inverse of the normal CDF with a singularity at both ends. And the quantized approximation is simply piecewise constant on uniform intervals, 2 to the d of them. Okay, so here, I guess this is with 16 intervals, I think, here. And then on the right-hand side, we've got the expected moments, both the second moment and the fourth moment of the difference between the quantized approximation and the true normal random variable. Now, this choice of approximation works quite nicely on a CPU, that if we take d equals 10, so that's 1,024 intervals, then what's required to actually generate the quantized approximation is you just need a 10-bit random integer, and then with that integer, you can do a lookup into a lookup table. And if you've got 1,024 numbers, if we're working, say, in single precision, that's 4 kilobytes. That sits comfortably in the L1 cache. And so that's a very cheap lookup process. So that's one approximation. The second one, which is my sort of personal favorite, is piecewise linear. But now, rather than being on intervals all of the same size, it's on dyadic intervals. So the intervals in each of the halves, from 0 to half and half to 1, they get progressively smaller as you approach the two ends. So they're actually, each of the intervals is halving each time. Turns out this is really good for vector execution on the CPU, that if you can do this with 32 subintervals, then you can actually look up both the mean and the slope of the linear, do essentially a table lookup, but you're doing it within vectors of length 32. And so it's very efficient. This is actually what I think Intel uses in their MKL software, except I think they probably do a cubic version rather than piecewise linear. It looks like it's quite complicated using these dyadic intervals, but actually you can get the interval index from the exponent of the uniform random number in the 0-half range. And so it turns out you can implement this really efficiently. And then the last approximation is just a classic least squares polynomial approximation. Now, this isn't going to be very good out at the two tails where it's singular, but it's adequate in the rest of it. And this is nice actually for GPU implementation with half precision, because there's no lookup table involved at all. So there's no sort of logic to be implemented. But the errors decay relatively slowly with increasing polynomial degree. So it's not a wonderful approximation. Yes, going back to these, I forgot to mention that here, the second moment and fourth moment come down more or less at the same rate. And that's because the errors are really dominated by what happens at the two singularities at either end. With the piecewise linear, the fourth moment comes down a whole lot lower. So here, the errors are spread so throughout the interval a bit better, and so the fourth moment is a lot lower. Yeah, the polynomial is not great. Okay, so how do we use that? Well, if we're just doing an SDE approximation with a fixed number of time steps, then this is really an example of doing the two-level multi-level. So here, the hat quantity corresponds to our standard Euler-Maruyama approximation using the correct normal random variables. Our p tilde corresponds to using the approximate random variables. And so again, we have this decomposition into a sum of an expected value using the approximates plus an expected correction. And in implementing this expected correction, you'd be using the same uniform random numbers U to generate both, the sort of true Z normal random variable and the approximate Z tilde being used for the other one. Okay. And then, with a bit of additional analysis, you can show that the variance of the difference in the output quantities, this is a financial payoff in the context of financial SDEs, scales proportionate to the variance of the difference between the true normal and the approximate normal. And so, as I discussed with the two-level method, you're going to get big savings if the variance of that difference is very small and the Z tilde is much cheaper to evaluate than the true normal Z using the inverse normal CDF. And in practice, you do see that. Okay, well, that gives it in the setting of having a fixed number of time steps. But really what we want to do is we want to get the best of both. We want to get benefits from doing multi-level applied to the time-stepping approximation, as well as extra benefits from using the approximate normal random variables. So how do we do that? Well, we do that by using nested multi-level. So we start by saying, classic sort of multi-level for SDEs, we have the expected value of p hat capital L decomposed into the telescoping sum. And then each of those expectations, we split it into an approximation using the approximate normal random variables plus a correction. Okay, so this term here splits into this pair. And this expected difference here between p hat L and p hat L minus 1 splits into this pair of terms. Okay, so hopefully that's all clear. So now we have this interesting four-way difference between true and approximate on levels L and L minus 1. Okay, and the approximate ones are being generated, computed in exactly the same way as the p hat L and p hat L minus 1. The only difference is I'm replacing the true normal random variables with the approximate normal random variables based on the same underlying uniforms. Okay, so that's the idea. There's then all sorts of fun with the numerical analysis. So this was a nice challenge. What we find is, well, there's this classic result for using the true normals, the difference between the path approximations on levels L and L minus 1 scales like the time step to the 1/2 power. You can show that the same is true for the difference between the approximate paths on levels L and L minus 1. Likewise, you can show that the difference between the true path and the approximate path on level L scales like the square root of the variance of the difference between the true Z and the approximate Z. And then the one that's tricky is this four-way difference, which, roughly speaking, behaves like square root of the time step times the square root of the variance. For those of you who are familiar with the literature on multi-index Monte Carlo methods, this is kind of what you would hope to get, that you get the product of the the behavior with respect to the time step, which we have up here, times the behavior with respect to the error in the random variables. Actually, more precisely, the theorem proves the following result, that for any q greater than 2, and you can think of it as just being very slightly greater than 2, then the root mean square error is bounded by a constant times h to the half times this expression. So the qth moment raised to the power 1 over q. So if we could take q equals 2, then that would be what I had up here. Turns out we have to take q to be slightly bigger than 2. Then we can look at, that says how the difference in the paths behaves. We can then look at what's the difference in the output quantity of interest. If the output quantity is a smooth function of the final path values, then we get an expression for the variance. In real financial applications, it's never that smooth. But if it's something like a financial put-call option where it's continuous piecewise linear, the analysis ends up being a whole lot tougher. The numerical results suggest that expression. We end up being able to prove this rather complicated expression at the bottom. So let's not dwell on that. Looking at numerical results, these are results looking at how the variance of these different terms behaves as we go down through the multi-level levels. So what I'm calling the baseline here is that's just the standard multi-level variance when we're using true normals. Okay, and it's coming down proportional to 2 to the minus 2L. And what I realize I've forgotten to put on this slide is the fact that in these numerical results, we're actually doing the time step in powers of 4, not powers of 2. And so that's why it's coming down like 2 to the minus 2L. Yes, that's right. And then these three below are corresponding to what I was saying on the previous slide in terms of the variance of this four-way difference. And they are likewise coming down roughly proportional to 2 to the minus 2L. The three different lines correspond to the polynomial approximation, which is the poorest. It's got the worst error. Then we've got the quantized one here. That's using the 1024 intervals with a piecewise constant. And then the dyadic is using the 32 intervals with a piecewise linear, and with the intervals shrinking into resolve the singularities. So, look at the sort of scale of this. We're talking about a factor 10 to the 5 difference in variance here. So really, the variance of these four-way corrections is small compared to the baseline variance. And so we will need to perform very few simulations using the true normals. In general, this baseline, you get virtually the same variance for the baseline using the true normals or the baseline using approximate normals. And so we end up using the usual number of samples up here on the baseline and relatively few of these four-way corrections to bring the accuracy back to being equal to the true normals. This is what happens when the payoff function is continuous piecewise linear. So this is a classic call option. And here you can sort of see a slight break in the slope, that it comes down initially roughly at 2 to the minus L, and then it sort of steepens up towards the end. If I sort of flick back between those, you can see that there's a bit less of a gap now between the baseline and the four-way correction. But still, you know, it's a considerable factor for the variance difference. Okay. Furthermore, we've got approximations now in terms of the normal random variables. We can also use approximations in the sense of doing reduced precision arithmetic. So, you know, instead of using double precision or single precision computations, if we're working on NVIDIA GPUs, half precision on those is twice as fast as single precision. And so, you know, what's the potential then of doing these calculations in half precision? So what we can do is use single precision for the p-hats using the true normals, and then use half precision for the p-tildes using the approximate normals. I would always do the averaging step in double precision, because otherwise you can accumulate considerable errors in the averaging process. And this links into other work where people have looked at this in the context of FPGAs, field programmable gate arrays, where you can really control the degree of precision you use for your floating point calculations. Okay. The thing that you have to be careful with doing the reduced precision is that you have to make sure the computations really are done in exactly the same sequence when computing the p-hat on its own, or when computing the p-hat that's needed for the difference. Sorry, I'm not quite sure what I said. When computing the p-tilde on its own, or computing the p-tilde in terms of the difference between p-hat and p-tilde, because you want the telescoping sum to work correctly. So you need this one in expectation to cancel out this minus p-tilde in expectation. So there's some slight subtleties there you have to be careful with. In terms of numerical analysis, you can model the effect of the half precision arithmetic in terms of the rounding errors as being this extra error term, where this delta has a magnitude of roughly 10 to the minus 3 for half precision. And you know, these are additional random variables VM, you know, that sometimes your half precision rounding errors will round up, sometimes they'll round down. And so this random variable here is reflecting the fact that on average, you have zero rounding error. Sometimes it's positive, sometimes it's negative. Yeah. So overall, that increases the variance by an amount of order delta squared over h. If this ends up being too large in terms of increasing the variance of the estimator for that four-way correction, then it's probably better not to use reduced precision. But certainly on the low levels, it is valuable. Okay, so what's the conclusion from this? So there's the nested multilevels. So that's certainly one thing I would highlight here, that this form of nested multilevel is more general than the multi-index Monte Carlo, but in concept is very similar. And that is a helpful way to combine approximate distributions with the sort of standard multi-level that we use for the time stepping. So offers significant computational savings. Oliver did actually later on in his thesis do some numerical experiments with the non-central chi-squared. That also worked well, but you know, the numerical analysis of that looks very challenging. And we never got round to doing multi-level QMC, quasi Monte Carlo, but you know, at some point I might like to get back to that and investigate that. Okay, some references. So these are some papers of Klaus Ritter, and Mario was a postdoc, and Lucas was a PhD student working with Klaus. Oliver and I have finished up this archive preprint, so we've submitted that now, and Oliver's thesis is also available. Okay, so let me ask if anyone has any questions. It's very quiet out there.